Um, Chip or Menominee, did you guys find some sheets printed on the table on the printer in the front there? Because maybe I didn't print it yet. Nope, I haven't.
No, we got nothing.
I'm printing it right now.
Oh.
Okay, the reviews are on the table by where Nick and Jake are sitting if you wanted to pick one up. The test is going to be on Monday. The test or the review is representative of the test. The test is a lot easier. I got to work on the review. I just haven't had time to get the review better. Okay, so yesterday we were dealing with logarithmic functions, and I tried to show you when you make the stair height the same. In a logarithmic functions, the lower stairs are very narrow. The higher stairs are much bigger. In fact, if you look at those two stairs, does it appear like the top one is about maybe 10 times as wide as the lower one? The lower one is this wide. The upper one, maybe 10 times that wide. That kind of makes sense. So if you go up one stair, you go over 10 stairs. So if you look here, if I make this go over to where 7 would be, which is, I think, I'm going to add 2 more zeros here. Oops. That didn't do it.
No.
I added them to the wrong spot. I got to add them in front of the decimal point. There we go. Nope, just 1 0. That'll do it. So if I add 1 more 0, you can see that the next step, when I go from magnitude 6, oh, I only printed 3 of them. Sorry about that. I'll print another one.
Thank you. Thank you.
You're welcome.
No, I'll leave mine loose.
Yeah, I don't know if there's a stapler over there or not. Sorry.
We got one. We're good.
Okay. So when I make the graph go up to 7, you can see that once again, the stair goes up 1 magnitude, but it also, once again, looks like maybe 10 times as far over. Okay, each step. Page. Let's go forward to C. We're on page 59, talking about the behavior of logarithmic functions still. The building in the picture, transcendental building, which is kind of cool. It's a T and an A. I don't know. I mean, that seems like that took a little architectural, coolness, right? Was designed to be earthquake resistant. Let's talk about the difference between resistant and proof. Like water resistant and waterproof. Anybody know that? Sam?
Well, my sister borrowed my windbreaker, which is water resistant, to go for a walk in the rain, and she came home completely soaked.
Okay.
Which was hilarious because I told her it was waterproof. So
way to go.
I mean, it's a mix-up. So, I mean, water resistant means it's not, you'll still get wet eventually.
Okay. So earthquake resistant versus earthquake proof. It'd probably be difficult to build a building that would be earthquake proof. You would have to figure out a way to make it as strong as, well, even stronger than the earth, right? Because the earth will crack and break. And so the design factors make it earthquake resistant. Now, a couple months ago, there was an earthquake in Indonesia. Does that sound right? Where a whole bunch of people died. And that was because their buildings were built too flimsy for the place where they were living. A better example, although it's not earthquakes, is that hurricane that went through North Florida. Did you see the pictures? Where almost every house was flattened, but there were a few that were like built out of concrete that were still standing. Nobody knows what I'm talking about. Okay. Do you know where North Florida is? No, I'm just kidding. Okay. Based on the data you've been working with, without doing any further calculations, how much more powerful is a 7 than a 6? Twice as much? 10 times as much? Somewhere in between. So we're going to vote on that. A 6 versus a 7. All in favor of twice as much, raise your hand. All in favor of 10 times as much, raise your hand. All in favor of somewhere between those two, raise your hand. How many people want the teacher to decide for them? Raise your hand. Okay. Let's look at the math and let's see if we can figure it out. The following table works with the questions in this section. If you notice, this is a table very similar to the one that we've been dealing with before. Notice it goes from 4 to 5 to 6, and they graphed it down below there. So here's a magnitude 4, here's a magnitude 5, here's a magnitude 6. On the graph, draw two line segments whose length represents the change from 4 to 5. Okay, so I'm going to have to sketch the graph here. I'm going to get my graph here. Oh, I'm missing a page. There we go. Okay, so we're sketching our graph. Here's 4. Here's 5. Here's 6, because these are the magnitudes. And these are the energies in gigajoules. And the energy in gigajoules goes up to 70,000. Okay, so it says that we should sketch a line. The change in magnitude from 4 to 5. If you will, start at the 5 and go down to the 4. You could start at the 4 and go up to the 5, but the problem is you'd be on the wrong side of the graph. Remember that our slope is always on the bottom side of the graph, never on the top side of the graph. So go straight down from the 5, straight down until you're even with the 4. That's the first line. And then it says sketch the change in energy from a 4 to a 5. So now start at the 4 and go over to the 5. So this is delta M, and this is delta E. And we have a very important thing that we know about those, and that is this right here represents the slope for a magnitude 5 to 4, and the difference in energy which if you look at the table, the energy for a 5 is 1995. And the energy of a 4 is 63.1. Okay, so that's the slope of the first one. Number 3. Now it says go from the change in magnitude from 6 to 5. So if we're going to do it the same way, where are we going to start? Where our graph crosses the 6 and go down to where we're even with the 5. Start at where the graph crosses the 5 and go forward until where it meets the 6, and you've got change in magnitude. Change in magnitude over change in energy. Number 4, based on your answers to questions 3 and 4, determine which of the following is greater. The energy between a 4 and a 5, or the energy between a 5 and a 6? Which one's greater? Between a 5 and a 6. Now, they asked the question, how much greater? They should be asking the question, how many times greater? Do you see the difference between those two questions? How much greater usually implies an answer like 47, okay? Whereas how many times greater, it'll be something like 6 times greater or something like that. Well, we know that the energy change between these two is, how much is that? 19, do the math. $1931. Is that right?
Yes.
Okay, or 1931.9, I guess. How about for the next one? Well, if you look at the energy for a 6, subtract the energy for a 5, so that's 63,100 minus 1995 divided by 6 minus 5. That energy change is going to be about 100. What do you get?
61,105.
61,105. So, if you are going to do how many times greater on your calculator, you will press the second one, 61,105, divided by the first one, 1932, let's say. And when we do that math, divided by 1932, it is 31.6 times greater. So I said 10 times as much. It's actually closer to 30 times as much, isn't it? Well, if we go back and did the math here, how much is this energy change here? If you take 1995 divided by 63.1, that also is 31 times greater. And if you take, well, we already did 63,100 divided by 1995, we also get about 31 times greater. So what's that saying? It's saying two things. One, it's saying this earthquake is, this one is 31 times more energy. Oh, I'm sorry. This one is 31 times more energy than this one. This one is 31 times more energy than this one. But it's also saying the slope of this one is 31 times greater than the slope of the other one. So, well, 31.6, I guess. So, if that is true, how would we figure out how much energy there will be in a magnitude 7 earthquake? Because that's not on our chart. So if we went up here to 7, okay, this is the point. How much energy will it be? How are we going to figure it out? What can we do? Ideas.
31.6 to the 7th power.
31.6 is the right number to use, but we'll just take 31.6 times how much energy there was at a magnitude 6, 63,100, and we get about 2 million. Two million gigajoules of energy. Page 63. If you've ever walked over Rofe Bridge or seen how such a bridge behaves in movies or on TV, you know how easily it can vibrate up and down. And we're going to study how those large vibrations happen. Now, my daughter says that new bridge that they just built down in Phoenix Park, anybody ever walked across it yet? Is it a little, shaky? Not really.
I guess kind of, but not super bad.
Not super bad, but it's not a suspension bridge either. It's a, steel structure bridge. But she said, yeah, it's a little shaky. So, what I've got here is there's a guy who's kind of afraid of rickety bridges. And so when he went on an adventure one time, he had to walk across a rickety rope bridge. Anybody know who I'm talking about? Who?
Not Indiana Jones, is it?
It could be, but I don't know. I've never seen that movie. This one I have seen.
Did you do that? Man, you gotta warn somebody before you just crack one off. My mouth was open and everything.
Believe me, donkey, if it was me, you'd be dead. It's brimstone. We must be getting close.
Don't be talking about it's the brimstone. I know what I smell, and there wasn't no brimstone. They come off no stone either.
Sure, it's big enough, but look at the location.
Shrek. Remember when you said that ogres have layers?
Why?
Well, I have a bit of a confession to make. Donkeys don't strap layers. We wear our fear right out there on our sleeves.
Wait a second. Donkeys don't have sleeves.
You know what I mean.
Oh, you can't tell me you're afraid of heights.
Oh, I'm just a little uncomfortable about being on a rickety bridge over a boiling lake of lava.
Come on, Donkey. I'm right here beside you, okay? For emotional support. We'll just tackle this thing together one little baby step at a time.
Really?
Really, really.
Okay. That makes me feel so much better.
Just keep moving. And don't look down.
Look down. Look down. Keep on moving. Don't look down. Don't look down. Keep on moving and don't look down. Shrek! I'm looking down! Oh, God, I can't do this. Just let me off right now, please.
But you're already halfway.
Yeah, but I know that half is safe.
Okay, fine. I don't have time for this. You go back.
Shrek, no,
Just
wait.
Donkey. Oh, let's have a
Wait,
dance
Shrek.
then, shall we?
Hey.
Donkey.
Ah, don't do that!
Oh, I'm sorry. Do what? Oh, this?
Yes, that!
Yes? Yes, do it. Okay.
Ah! No, Shrek! No!
Stop doing it. I'm doing
Oh,
it.
God, I'm gonna die. I'm gonna die. I'm gonna die. Shrek, I'm gonna die.
Oh. That'll do, Donkey. That'll do.
That'll do, donkey. That'll do. Okay. That's one of the videos, but this one is actually a little bit more scientific.
Beautiful, light, and flexible, the Tacoma Narrows Bridge was built like no other suspension bridge. It was unique in its design and incredible in its appearance. But on November 7th, 1940, it all came crashing down. The collapse was one of the great tragedies in engineering history. Never had a suspension bridge so important met its end so catastrophically. But the Tacoma Narrows Bridge's true legacy was not in the frantic headlines generated by its collapse, but in the revolutionary changes it brought to the world of engineering and bridge architecture. That was Galloping Gertie's triumph. In the 1920s, America was prospering and optimistic. Skyscrapers and bridges were seen as symbols of elegance and power. Then, with the 1930s depression, cheaper and more efficient bridges were needed. As a result, bridges were made as simple as possible, graceful and slender works of art, beginning a trend towards light, flexible bridges. The Tacoma Narrows Bridge was proposed to connect the Olympic Peninsula and the Washington mainland. The Washington State Department of Transportation appointed Clark Eldridge to design the bridge. Eldridge's plan was examined by an out-of-state engineering consultant, the world-famous suspension bridge designer Leon Moseff. Moseff suggested replacing the 25-foot-deep stiffening truss with an 8-foot shallow plate girder. Conforming to the trend, this lessened the cost of the bridge and gave it a slender, artistic appearance. In 1939, construction of the $6 million bridge began. On July 1st, 1940, the Tacoma Narrows Bridge officially opened. It was the third longest suspension bridge in the world. Thousands of people attended the ceremonies. Thousands more worldwide were intrigued by the bridge's extraordinary width-to-length ratio and its exceptional flexibility. But the Tacoma Narrows Bridge had an even more fascinating characteristic: its bounce. Engineers were puzzled by these strange oscillations, but they did not doubt the bridge's safety. In fact, the bridge's movement attracted thousands of people who crossed the bridge just for the exhilarating experience of watching the car in front of them disappear. For this, the Tacoma Narrows Bridge was quickly nicknamed Galloping Gertie. Galloping Gertie proved to have many more benefits. It linked the less developed peninsula to the industrial Tacoma area. There was rapid land development and population increase. The bridge also benefited the military, connecting the McChord Airfield and Puget Sound Navy Shipyard. All around, the bridge was a marvelous success, but Gertie began to run into problems. The engineers grew more worried about the bounce. Leon Moseff was contacted, but he assured them that it was not a problem. The engineers hired Professor F. Bert Farquharson at the University of Washington to build a scale model of the bridge and test it, while also studying the real bridge. We knew from the night of the day the bridge opened that something was wrong. On that night, the bridge began to gallop. Attempts were made to control the motion by installing hydraulic jacks and tie-down cables, but these proved ineffective. Farquharson observed a torsional twisting in the bridge model, different from the regular bounce. He recommended adding wind deflection devices, and preparations were made to install them, but the bridge did not meet nature's deadline. On the morning of Thursday, November 7, 1940, winds whistled across the Narrows. The bridge was rolling 2 to 5 feet. Suddenly, the bridge went into a lateral twisting motion. The sides rose and fell 28 feet up and down every 5 seconds, tilting at a 45-degree angle. Leonard Coatsworth was on the bridge when it began its violent twisting. He got out of his car and fled the bridge. His dog Tubby was left in the car. Farquharson arrived to record the event. The bridge had been closed by officials alarmed by the dangerous motion. Observers were worried, but very few expected what would come next. The first section of concrete from the center span broke off. The bridge began a violent motion. Steel girders twisted, cables snapped, lampposts broke off, and pieces of concrete fell. Then, 2 minutes later, a 600-foot portion of the center span plunged into the Narrows. Howard Clifford, a newspaper photographer, was one of the last people on the bridge.
It was bouncing so that it would go up where I was, and then it would snap down so fast, and I would drop as fast as that went down. I would be going down. This was coming back up, and it hit me every time and knocked me down.
Along with pieces of the deck, Leonard Coatsworth's car and dog fell. The dog was the only casualty of the collapse. 11:10 a.m. saw the end of it all. Galloping Gertie hung limp and broken. The hopes it had inspired had been crushed. The tragedy was complete. Gertie's collapse came as a shock to the public. Many people were angered, blaming it on faulty engineering. They felt that their tax money had been wasted, and more would be squandered for conducting studies and rebuilding.
Nobody thought it would go down, no. I mean, if they thought it was going to go down, they would have closed it right away and tried to figure out what to do.
Several committees were appointed to analyze the cause of the collapse. The Federal Works Administration set up a group of professional engineers. In March of 1941, they announced their findings in a report. Part of the problem was that the solid plate girders on the side caught the wind like sails. The original truss design would have allowed the wind to pass through harmlessly. Also, due to its exceptional width-to-length ratio, the bridge was extremely flexible and fragile. Still, the winds had not been overly powerful. In fact, they scarcely exceeded 42 miles per hour. So what did prompt it? As the wind passed over and under the bridge, it created vortex shedding, where wind eddies formed on the opposite side. These eddies gave small pushes to the structure. Although the force wasn't especially great, the vortices caused the bridge to sway rhythmically. Eventually its motion became self-excited, meaning that it propelled itself. The bridge's drastic motion was caused by harmonic resonance. The basic idea is that everything vibrates at a natural frequency, which can be approached by outside forces. This concept is illustrated by a mathematical theory later suggested by Theodore von Karman. On that day, the frequency of the wind was close to the bridge's natural frequency. This resulted in a very small denominator, which made the amplitude of...
So, do you remember yesterday when we were doing the, or maybe that wasn't in this class, that we were doing the, when the denominator is 0, bad stuff happens? So if you take the natural frequency of the bridge and you have the frequency of the wind eddies, and those two get very close to each other, they're going to cancel each other out, and then you're going to have no denominator, which means you're going to have big problems.
The motion huge. Unfortunately, such science and mathematics were overlooked at the bridge's construction. Galloping Gertie's collapse drew attention to them, and it continues to be a challenging puzzle for engineers all over the world to study and learn from. When Galloping Gertie collapsed, hopeful newspapers speculated that it might be rebuilt within the year. Then, World War II struck, and Gertie's remains were seen as a valuable mass of steel, and the state paid workers to salvage the material. Meanwhile, Farquharson had conducted groundbreaking studies on the model bridge, greatly advancing wind tunnel testing. British engineer W. Austin came to study the Second Narrows Bridge to help plan an English suspension bridge. Quote, "The whole of bridge engineering has profited by the fall of the Narrows Bridge. The subsequent research at the University of Washington is one of the most significant steps in bridge design in many, many years." Indeed, the Tacoma Narrows Bridge was followed by the Mackinac Strait Bridge and the Verrazano Narrows Bridge, both benefiting directly from the lessons it taught. Before launching plans for a second bridge, it was decided that the solution to offer least wind resistance was an open stiffening truss. No expense was spared in building the second Tacoma Narrows Bridge. The bridge had 33-foot stiffening trusses, wind grates, and hydraulic shock absorbers. It was the most technologically advanced bridge of the time, and the years of research in aerodynamics and mathematics triumphed in enriching the science of bridge engineering all over the world. A writer called the second Tacoma Narrows Bridge epoch-making. Galloping Gertie's sequel, fondly nicknamed Sturdy Gertie, set the standards for modern bridge design, terminating the trend of lighter, flimsier bridges. Wind tunnel testing is now mandatory for all suspension bridges. The second Tacoma Narrows Bridge picked up where its predecessor had left off. The tragedy of Galloping Gertie's collapse led to triumph, revolutionizing science and architecture, directing the change from light, flexible bridges to strong and dependable bridges, and bringing a wealth of new knowledge to the engineering world. And although an unprecedented initial success resulted in tragic failure, the Tacoma Narrows Bridge rose to triumph in the end. Stable, safe, and still beautiful, Sturdy Gertie remains as a lasting testament, power achieved by grace and artistry, and a triumph that has shaken itself out of the ashes of tragedy.
Okay, a couple things that I want to stress about what they said in the movie. First off, at the very beginning of the movie, they said that it had 25-foot wide sections under the bridge. So this would have been like down here under the bridge. 25-foot wide, and they called them trusses. Now, I don't know if you're acquainted with what that means, but all it is instead of being solid, like a floor truss or a floor cross member would be, with solid wood, they just have crosses all the way across it. That was the original design. Then a guy came along and said, well, make them only 8 feet wide and make them solid. Now his thinking was, well, if it's solid, it's going to be stronger than if it's just the cross members. But the strength of a beam comes from the top and the bottom, not from the middle part. So they made them instead of 25 foot wide, they made them 8 foot wide, and they made them solid. Now, it wasn't the wind blowing on this side, it was the wind sucking on the other side that kept them up. Anybody ever fly a kite? The kite doesn't fly because the wind blows it up. It flies because the backside of it is curved out and there's lower pressure on the backside. So those eddies were what was causing it. Well, if you noticed, here was the original construction was 8 foot wide. When they rebuilt it, they said they made those trusses 33 foot wide. If you noticed, that width was just dwarfing the size of the trucks that were going across it. Did you see that? But the other thing that was true is that the original bridge was very, very narrow compared to how high or to how long it was. The second bridge was much wider compared to how long it was. All of that contributes to the shape of the function that the bridge has. Now, in this case, they have frequency and the amplitude of bridge vibrations. Remember that formula that they said amplitude of bridge vibrations was related to the wind speed and the natural harmonic motion. Okay? We'll just talk for a minute about that idea of natural harmonic motion, natural harmonic frequencies. And that is like anything that you hit has a natural harmonic frequency. That's about a low D right there. Okay? This desk here, much different, right? You can hear the difference in the pitch that it has. So all of those things have a natural frequency. Well, the bridge's natural frequency was just at the right speed for the eddies that were formed that day. And the day was November 7th, 1940. Well, I remembered something. I wasn't around, but I remembered something from around that time. Oops.
I'm meteorologist Mark Mancuso, and on this day in weather history, November 11th, 1940, the Armistice Day blizzard hit the Midwest region of the U.S. An intense low-pressure system tracked from the southern plains northeastward into Wisconsin, pulling Gulf moisture up from the south and pulling down.
Oh, it's reloading? No. That's never happened before.
Pulling Gulf moisture up from the south and pulling down.
Oh, let's see if we can get past it. I know what's wrong.
Then sleet and snow began to fall. The intense early season Panhandle Hook winter storm cut a 1,000-mile wide path through the middle of the country from Kansas to Michigan. Brought up to 27 inches of snow, accompanied by 80-mile-per-hour winds. In Watkins, Minnesota, 2 trains.
I don't know what's going on. Never had that problem before.
Turkeys intended for Thanksgiving dinner across Minnesota perished from cold exposure. On Lake Michigan, dozens of sailors died on small boats and 3 cargo freighters. Along the Mississippi River, hundreds of duck hunters were caught in the storm. Due to a poorly predicted forecast, they were ill-equipped for the conditions. Many took shelter on the small islands on the river. But the 50-mile-per-hour winds and 5-foot waves overcame their encampments. Dozens froze to death in the single-digit temperatures that night. It caused 154 fatalities and $2.2 million in damage at the time. I'm Mark Mancuso.
So what happened was that exact same storm that caused the bridge to collapse affected the weather here in Wisconsin and Minnesota too. Now they said that the snow came up from the south, but it met with that wind that was coming from the west, and so it caused that blizzard type situation. I don't know, interesting stuff. All right, so we've got a function here that is not linear, it's not exponential, it's not periodic, it's something else. And what they want you to notice is that something else is still a function. What's the proof from the graph that it's a function? Yep, the vertical line test. Every place you drew a vertical line, it would hit the graph only one time. Now, this bridge has a natural frequency of about 0.45 meters. How do I know that? That's where the highest peak is. So the Tacoma Narrows Bridge, if you noticed, its amplitude was quite a bit different than that. It was probably, 10 meters, 15 meters. It looked really big, didn't it? When that thing started vibrating. But that's because the bridge was much larger. So what I want you to do for today, let's look here down at the bottom of page, what page is this? 63. While it is true that someone stomping on a bridge or forcefully jumping up and down will cause large vibration, it turns out what is really critical to causing large vibrations is the frequency of the stomping. In this activity, we'll be focusing on the frequency of steps that a person takes, that's the horizontal axis, while walking across the bridge. A hertz is a wave per second. So 3 hertz would be tum, 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 tum. You're vibrating about 3 times per second. The amount by which the bridge moves up and down is the amplitude, and they say the maximum amplitude is about 0.45. So what they want you to do is to look at the table and the graph and start answering these questions. And I believe you can answer question 1 and question 2 and question 3. Go. Nick. Michael.
Yep.
Marlena. Gavin. Janae. Felicia. Nicole.
Yep.
Eric.
He's here.
He's here.
Phil.
Yeah.
Grant.
Yep.
Hunter. Paige. Eric.
Present.
Laura.
Here.
Madeline said she was going to be here. Sarah.
Here.
Bailey. Jessica.
Here.
Lauren.
Here.
Jake. And Sam.
Yep.
Okay. Okay, question 3. When you walk at 1 step per second, so 1 step per second, what do you get for an amplitude? .296 meters. If you walk with a frequency of 3 steps per second, 3 hertz, what do you get for a frequency? I'm sorry, an amplitude, sorry. Well, if you look at the chart, does 3 appear on the chart? No, so it's going to be somewhere between 0.187 and 0.142, closer to 0.187, right? The other way, though, that you can do it is if you go to the graph, and you can see that a frequency of 3 looks to be about 0.1. Did anybody say 0.175? Okay. Number 4, or I'm sorry, just above number 4. The frequency that a typical human walking can be as low as 1.5 hertz, and the frequency of a typical human running can be as high as 2.8. So if you look at the graph from 1.5 to 2.8, what do you see on that bridge? 1.5 to 2.8. The amplitude is the highest during those sections, right? So the bridge was built for something other than walking or running across, wasn't it? Because its biggest vibrations happen when you run or walk. Page 65, it says, let's fill in the missing data on the chart. Okay, so let's look at the first one there. So they say, well, let's start at the interval from 1.5 to 1.6. Well, at 1.5, the frequency is the amplitude is 0.391. At 1.6, it's 0.414. Why did I take 0.414 minus 0.391? You always take the second value minus the first value divided by my second frequency, which is 1.6, minus the first one, which is 1.5. When I do that math, parentheses, 0.414 minus 0.391 divided by parentheses, 1.6 minus 1.5, and I get 0.23. So my table says that the rate of change in amplitude is 0.23. So in this section of the graph, where I went from 1.5 to 1.6, this section of the graph right here, the slope was 0.23. Does that slope make sense? First of all, it's going uphill, which means our answer should be positive, right? Lauren, why don't you sit next to one of the groups? How about these guys over here, and then you can work with them. Okay, so fill in the rest of the rates of change in amplitude, and then we'll go on to number 5 when we get done with that. Okay, so what did you get for 1.6 to 1.7?
0.21.
And how about from 2.2 to 2.3? Negative 0.23. And then 2.4 to 2.5?
Negative 0.41.
And 2.7 to 2.8. So did everybody get those filled in now? Okay, so I graphed, in Desmos, I graphed the function, and I graphed the rates of change for each of the different points along the way. And I think what's interesting about it is, you can see in the green here that the biggest rate of change was around this spot here, which is where the slope is the steepest. The biggest negative rate of change was somewhere in here, although it looks like this one is also pretty big. It's possible that the calculations were caused because the points that they chose were different widths apart. I'm not sure. So we've got a positive slope up till this point right here, and then we've got a negative slope until they both kind of even out and eventually get towards zero, the more frequent the oscillation, which kind of makes sense. Because if you start going, you're going to be vibrating so fast that you couldn't affect the bridge no matter how hard you tried. Number 6. Which causes a greater change in amplitude? Changing from 1.5 to 1.6 or from 2.2 to 2.3? 1.5 to 1.6, 2.2 to 2.3. What did you notice about those two? They're the exact same, right? Except one of them is negative and the other one is positive. Isn't it 0.23? Is 1 point? This one is 2.2 to 2.3. This one is 1.5 to 1.6. Is 0.23. Only it's negative. Okay. And then, so any of these 0.1 changes in pace produces these different magnitude changes, and it looks like the biggest positive one is right here at I must have made a mistake when I did this second chart. 0.2, 0.4. I don't know where I got those numbers from. I don't know which 0.1 change was the biggest number when you did the math. Number 7. This one right here is pretty big, right? Negative 0.4.
But then 2.4 to 2.5 is negative.
How big a negative is it? Negative what?
0.41.
Negative 0.41, so that is slightly bigger. So the pace of walking that would produce the largest vibrations in the bridge, let's go back to the graph, would be 1.9. Is that right? That's the largest, right? Given the frequency of a typical human walking, do you think that this bridge is well designed? Certainly not well designed for people who are going to be walking across it. Okay, when we come back, we will start linear functions.
What's the something there? I'm not sure. Yes.
Did everybody get a review? Everybody took one?
Monday. Is it open right now? We're taking it. Person.
Is it doing all this stuff?
Probably.
He's the last one.
Yeah, I got like 2 hours to do it now. It's true. Oh, it's so good.
Okay, linear equations.
Really want a shirt.
We're on lesson 5A. Verbal linear equations. Let's look at the one that they talk about. Colleges charge tuition to their students. What does the tuition cover? What'd you say? Good question. Paying for the teacher, that's important. Paying for the building, that's important. Paying for the books, not at CVTC. There are some colleges that it pays for the books. Stout, at least used to, they called it textbook rental, but and Eau Claire does for undergrads. Then it says, do you know how much you're paying for tuition? Some people do, right? You're taking this class as part of a decision you've made to transfer to another institution. Anybody have any ideas why you decided to do that?
Cheap.
It's cheaper to go to CVTC. Yeah, that's not a bad reason. Save yourself money. I have, let's see if I can find my tuition. Oh, I know where it is. I'll try here, but I don't think it's here. It is not there. Okay, let's try here. Tuition. I saved my bill for when I went to the university a little while ago. There it is.
At Eau Claire?
Yeah, Eau Claire. So
Really?
here was my tuition. $2,997.12 for a 2-credit class. Let's close current one. Let's see here. I got another one here. Let's see what this one says. Nope, that's not it. Thought.
Was it a good class?
Well, should have been, yeah.
Yeah.
Let's try UWEC. So I think
3 months of pay.
here's my grad transcript. That's not what I'm looking for. Payment plan. Summer bill. That might be it. When I went to school during the summerette. So I took that was only $1,449 for a 3-credit class. What's that?
It's a bargain.
It was a bargain, yeah. $146 for fees and then $1,200 for tuition. So one of the things that it says here is that, do you also pay fees? Hey, at CVTC, do you pay fees? Well, there's a registration fee you have to pay, but there's another fee. You pay a parking fee as part of your tuition. So whether you drive a car, own a car, or not, you get a parking pass.
Our parking is free.
What's that?
Our parking is free.
In Menominee.
Oh, they have.
They are free. You don't have to pay for them.
That's
But they
right.
charge you a fee that is like, I don't know. Let's see how much the parking fee is in Eau Claire at CVTC. Excuse me. Sorry about that.
I go to
CVTC.edu.
Supposed to have a parking pass.
Yeah.
I'm just going to check the thing here
Yeah, but you pay
for
for it when you pay for it.
parking fee. Oop, not feet. What does it say? Get a parking permit. Tuition is defined as program fees, parking fees, supplemental fees. Doesn't say how much that parking fee. Oh, here it is. Public safety fee, $3 per credit. So that's how much you pay for a parking pass. So for this class, you're paying $12 to park in the parking lot. And now I think that's at Eau Claire, so I don't know what they charge you guys in Menominee, to be honest with you. If it's $12 a credit or not. But if you notice, tuition is, for this class, is a little bit more expensive. It's about $50 more a credit than other credits that you take. And I use that money to fund my fishing trips. If I get $50 from each one of you for each of the 4 credits, that's like $200. I should retire on all the money that you aren't paying it to me. That would be awfully nice if I would get that money. There's a lot of people that money goes to support. Okay, so we're talking about tuition, and we're talking about going from verbal into linear equations. Question number 2. Cisco Junior College states on his website that tuition is $90 per credit hour for an in-county resident. So for question number 2, we're going to start with the words $90 per credit. And we're going to see how to make interpretations based on that. So, do part A, B, C, D, and E. Go.
Way to go.
Does somebody still need the book up? Does everybody have their book?
I could use it in Menominee. My computer died. So, he's getting it up.
Laura?
What was that?
I said, are you getting? No, I was kind of vegetating there for a few seconds.
Yeah,
I'm going to now. I'm back on track now. Had a fun little siesta. Now I'm going to get to work.
Yeah, I feel like. Anybody need some more time? Lauren, you got them?
you needed some help.
Where does it say the additional charge?
Well, since it's $90 per credit,
Yeah.
so which question are you on?
Well, I was going through this one from there. It seems like we-
Okay, let me see what you did for this one over here. Yep, that's right. Okay. So it cost, he was 3, now he's 4. 3 was how much? 3 credits was how much? You can look back, because you just did it. And 4 cost $3.60, so how much more?
Oh.
Eric, is that vodka?
No, it's asking how much more.
Okay. Okay.
Do a lot of vodka before that.
Okay. 2A. How much does it cost to take a 3-credit class? $270. A 9-credit class? Part B says Albert signed up for 3, so he was paying $270. Now he decides to add an additional, so how much is he paying now?
$360.
So how much does the additional extra credit cost him? $90. So when you go from 3 credits to 4 credits, the rate of change is $90, right? Part C. Mata signed up for 9 credits and decided to take an additional 1. So how much was the new tuition? How much was Mata paying? $900. So when you go from 9 credits to 10 credits, how much more did she pay than before? $90. So the rate of their change there was $90. Part D. For each additional credit, what is the additional tuition charge?
$90.
Is the relationship linear?
Yeah.
Because? Good. The rate of change is constant. When you look at a verbal equation, a verbal representation, look for the word per. The word per, or the number before the word per, is the slope. And remember, the slope is always going to be 2 things. In this case, dollars per credit. So when you have a verbal representation, that's how you can interpret the information. The next one is not a verbal representation. Tuition at Dallas County Community College is also calculated using the number of credit hours. So now we're going to go from a table for a linear equation. The first thing they want you to do is to fill in some information on the chart, and then on the next page, answer parts A, B, C, and D. Okay? Go. You looked at me like you needed help with that one, but
No.
okay.
Oh, sorry. Roku. Just bought Roku yesterday morning. Volatile lunchbook. Roku is on that Roku TV.
Yeah, and kind of the more right now is changed. Like for long-term investment stuff.
Were we supposed to write a formula for the last one?
Yeah,
We'll have to do that.
I put $50 a week in the AT&T. So like,
Anybody need more time, or is everybody ready? Here we go. Number to the last part, we should have said tuition is 90 per credit. Or we could say T as a function of credits is 90C. I don't remember if they wanted us to make it a function notation or if they wanted to write it as a function. So we should have written it this way. Okay, next one. They want us to fill in the cost per additional credit hour. So cost per additional credit hour. So in other words, in the first case, we don't know the additional credit, but for the second one, we don't know what it was additional from. But for the second one, we will take $104 minus $52 and get $52. Oops, I can't see that. For the third one, we take 156 minus 104 and we get 52. 208 minus 56 and we get 52. And about this time, I was looking at your papers, and just about everybody by this time had done this. Does that describe your actions? Okay? So we would say in a table, the rate of change is constant. Cost per additional credit hour. So, part A says she signed up for 6, she adds 1. What was the increase in her tuition? $52, right? That's the rate of change between 6 and 7. B, fill in the last column, we did. C, what is the relationship between tuition and credit hours? Multiply the credits by
52.
By 52. Write a formula that describes the relationship. Well, this time they don't want us to write it as a function. They just want to write it as a formula. T equals 52C. Or we could write it as a function. T of C is 52C. Everybody good with that? Number 4. From a verbal to a table with a y-intercept. Let's look at this problem here. Some colleges charge students additional fees, such as an ID fee or registration fee. Wharton County Junior College, for example, charges in-district students $32 per credit hour and a total of $111 in fees per semester. So if you take one class, you pay for a credit plus the $111. Two classes, you pay for 2 credits plus the $111, and so on. Okay? So fill in the chart and then answer the questions about up through letter D.
Ooh, should walk roughly 10 minutes.
You know how to do those rates of change there, Connor? I'll do the first one for you. What did you get for a total here?
143.
What did you get for a total here?
175.
The rate of change is always the second one minus the first one. So in this case, it'll be 175 minus 143. But then you have to divide it by 2 minus 1, which is, what'd you get? 175 minus 130 what?
32.
$32 a credit. Now, why didn't you have to worry about this 2 minus 1 business?
Because it'd be divided by 1 anyway.
Okay. As long as these numbers are 1 apart each time, you don't have to do the division. You see that?
Yeah.
Because if they stay 1 apart, that denominator always changes by 1, so you can kind of skip the denominator part, since dividing by 1 gives you the same thing. Why didn't you have a rate of change for this first spot right here? Yeah. So you will never fill in a rate of change in the first box in a table. You can't fill it in because there's nothing to subtract it from. You can only go to the second one down, and the third one down, Now, I suppose conceivably, all the people in America pay $111 to Wharton College because they are taking no credits there. But it would be difficult for them to collect it from me. So I'm not going to let them know that I exist. Okay, so let's go through the table. And remember, the important difference this time is we're still filling out a table, but now there's a y-intercept. A y-intercept means you have to pay something at the beginning. Remember when we were doing the line of people? No, that wasn't in this class. It was in a different class. Well, anyway, this is the first time that we've run across a cost for doing nothing. Because at the first college, it was $52. No, that was the second one. First one was $90 a credit. Second one was $52 a credit. This time, it's $111 added on to however many credits you have. So if you notice here, what are we doing in the table between the first and the second column? I've got the little symbol there, which tells us we're going to multiply, right? Multiply by what? 32. So the first time it's 32, 64, 96, 128, 160, 192. Is that what everybody got? But here's the question that somebody was asking is, when we add on the $111, do we just add it on the first time? No. Everybody pays $111, whether they take 1 credit or 2 credits or 3 credits. Everybody adds on the $111. So their total comes out to be $143, $175, $207, $239, $271, and $303. For this one, we're going to take 207 minus 175, and we get $32. 239 minus 207, and we get $32. Is that what you got in every case? 271 minus 239 is $32. 303 minus 271 is $32. So, does the $111 change anything about our function? I mean, about the slope of our function? No, it just moves our graph up $111, right? Okay. So the distinguishing characteristic this time is, how do we write tuition as a function of credits this time? Well, I believe this is the cheapest tuition that we've had so far. How can I tell it's the cheapest based on this value right here? It's the smallest number, right? The first one was $90, the second one was $52, this one is $32. If we were going to graph it, of course, 32, 52, 90, they're going to be steeper, right? The more you get for that. So, $32, but we have to remember that it's shifted $111 up. We call that the y-intercept. Oh, they want it to have it be t as a function of h. I don't like calling them hours. Comes from talking to a high school teacher, and they say they teach whatever 6 hours a day. They don't, because an hour in high school is like 44 minutes or something like that. And ours aren't an hour long either. Can you imagine how much unrest there would be if I kept you here for an hour? You'd be like knocking on the president's door saying, that stupid Kevin kept me here until 11 o'clock rather than 10:55. Okay, so we call them credits rather than hours. Page. '71, we're going to start talking about a different way to write a function, and that is we're going to start out with a table and see if we can go to a verbal equation. On average, how many steps do you think you take each day? Does anybody have one of these pedometer thingers that they keep track of their steps? None of you guys do. How many steps do you take each day? 15,000? What'd you say?
10.
10,000? Or 10 steps?
Just 10.
Some days I get out of bed and some days I don't. What do they recommend you take each day? 10,000 steps a day. Now, then it says, what does that mean in terms of miles? Well, if you spoke Latin, that would be just an easy equation to make. The Latin words 1,000 paces is milia passuum. Mile, pace, you get it? A mile is 1,000 paces. Well, let's think about it. In Rome, a pace was lift. So it's actually 2,000 steps. 1,000 paces is 2,000 steps. So if you go 10,000 paces, 10,000 steps, you will go 5 miles. Okay? Kind of interesting to keep track of that kind of stuff. How many steps should an active person take? 10,000 a day. Let's look at the next table here. On the next page, we are going to go from this is 5B. We are going to go from a table to a graph. Go. When you graph those dots on there, you can go to the next page. There's the graph is right there. When you put those dots on your paper, I saw a number of you were tempted to take those dots and play dot to dot back when you were in grade school, which probably helped you realize why we call this a linear function, right? Because the dots form a line, a straight line. Now, one of the things that I don't like about if we were to connect them with dots, if we were to connect the dots, I'm going to zoom in here. That's not how you zoom in, Kevin. Let's see here. Okay, so here is no, I have to get even closer, don't I? I'm going to make it so that my graph goes from, x goes from 0 to, my x-axis goes from 0 to 1 minute. And my y-axis goes from 0 to 3 steps. I want you to notice here, that's not 3 steps. 0 to 3 steps. I better change this to about 10 seconds, so 0.05. Let's do it that way. Okay, so I wanted to show you something that is absolutely crucial to understanding it functions. We showed this to be a line on here, correct? Here is 0 steps. Here is 1 step. The line makes it seem as though you can take 0.5 steps, 0.2 steps, 0.4 steps, 0.6 steps. You can. You are either here, or you're here, or you're here, or you're here. So they really should have had dots all the way along there. Just fun facts to keep in mind. Page 72 on the graph. So when we came from the table had equal rates of change. The graph the dots were in a line. But now it says something else here on page 72, part B. Explain how the graph is telling us that he's walking at a constant pace. How does the graph show us that? The rate of change is constant. Okay, so all of those are different ways to say that something is a linear function. So let's look here at the table for part C. See if you can fill in that table on part C. Go. Okay, y did they have this first one? Why did they say not applicable here?
And 0 steps taken.
And there's nothing to subtract it from, right? So, for the second one, we would take 600 minus 0 over 5 minus 0, and we get 120, right? 120 steps per minute. And you can find that by the graph also. This will be the minutes, and this will be the number of steps. So you can always take the y-axis thing over the x-axis thing, and that'll give you this slope also. Next one, 2,400 minus 600. Hey, I thought that the difference was always the same. Remember, it was always like $32. This time the difference isn't 600 like it was on the first one. This time the difference is 1,800, right? 2,400 minus 600 is 1,800. Why did the slope work out to be the exact same, even though the differences were so much different? Let's look at the graph. I'm going to go out to 0 to 35 minutes, and I'm going to go from 0 to 5,000 steps. Oops. 3,500 steps, that'll be good enough. So for the first one, we found the slope between these 2 points. For the second one, we found the slope between these 2 points. Does it make sense that the number of steps will be much, much bigger? Because the number of minutes is also much, much bigger. In each case, did you get 120 steps?
Yes.
New concept. The change in the rate of change. So we're going to be talking about how the rate of change changes. Okay? Each case it was 120. Well, what is the change in the rate of change? Notice we have nothing to subtract from here, obviously, but we also don't have anything to subtract from here. In the third one down, we can take 120 minus 120. How do you get the rate of change? Well, you take the old rate of change, the new rate of change minus the old rate of change, and you divide it by the second time minus the first time. So in this case, we'll divide it by 20 minus 5. What do we get? Zero divided by 15 is 0. Next one down. 120 minus 120 divided by 25 minus 20. What do we get? 0, correct? Last one. 120 minus 120 divided by 35 minus 25 is 0. Got it? Page 74. For each linear equation you found in question 2 and 3, write the steps in the appropriate spots in the diagram. Oops. Oh, we didn't do that yet. Sorry about that. So, part E on page 73, S as a function of time is 120 times the amount of time that you walk. Fernando decides to regularly walk at lunchtime to stay fit. He finds that a brisk walking pace is 3 miles per hour. However, his walking app only gives him information about the number of steps, not the distance he walks. He finds that walking 2,000 steps briskly is the same as 1 mile. So if he takes 4,000 steps, how many miles does he go? Well, 4,000 steps times 2,000 steps is 1 mile. He goes 2 miles. 6,000, how far would he go? 10,000. So if he takes 1,000 steps, how far would he walk? 0.5 miles. So what do you do to the number of steps to determine how many miles you walk? Miles as a function of steps is the number of steps divided by 2,000. So fill in the table there. Steps and miles. 0 steps is 0 miles. 600 steps? What? 0.3 miles. 2,400 steps? 1.2. 3,000 steps? 1.5. 4,200 steps? 2.1. He decides to combine this information to determine the number of miles he walks in terms of the time that passes. So for part A, he inputs the number of minutes, time. He puts that into his machine, and his machine says, oh, I know what to do. I will multiply by 120. So what does he get out if he multiplies by 120? 120 t. He takes that information and puts it into the machine, 120 t, and the machine takes that and divides it by 2,000, and so his number of steps will be 120 t divided by 2,000. Does anybody want to simplify that any?
Yeah, you can divide them both by 40.
Yeah, you could just do it as a decimal. 120 divided by 2,000. We could say that our coefficient is 0.06 t, or in other words, you go 600ths of a mile per minute. What is the relationship between the output of 1 and the input of 2? They are the exact same thing. So after 5 minutes, we would multiply by 0.06, and we would find he would go 0.3 of a mile. My question to you is distance as a function of time, in this case, is this a linear equation? Anybody know why?
Just the rate
It
of
is
change.
linear because.
The rate of change is constant.
Okay. Rate of change is constant, and that's this part here. But more importantly, time is to the first power. All right, we've got about 5 minutes left. Let's take out our reviews that I handed out and work together and get through as many of them as you can. Go. If you need help, let me know, and I'll help you. It is in class. Yep.
Is it the whole hour?
No, it'll probably take us about 15 to 20 minutes. Nicole.
I'm not sure.
Okay.
Oh, R. That's the what it says the dependent variables are. Which one?
Number. Okay. Change in height between T1 and T2 is, so the change in height is T2 minus T1.
Consider if you have a graph, you would have.
I'm sorry, this one?
For time.
It's the second.
Okay, here's the thing to remember. Yes.
Input. Time is input.
Always comes second. This always comes first.
Is the test like, so if it's like.
It's multiple choice. They are all multiple choice.
Circumference divided by 2 pi.
How to explain?
No.
Okay. So like, I don't know how to explain time.
So I chose C because C is my favorite letter ever.
Yeah.
And I'm sticking to that as my answer. And I'm not going to change it. I've often wondered if I should go around and say there are 14 B's on the test, 3 C's, and then you would go through and say, ooh, I haven't had enough D's yet. So I better guess a D. I've often wondered if I should do that.